The neutrino puzzle solved. Augmented Newtonian dynamics. Introduction. For almost a century, neutrinos have been the ghost particles of physics, invisible, almost impossible to detect, and thought to carry a tiny but uncertain mass. Physicists still cannot pin down exactly what they are. And theory offers a very different answer. Neutrinos are not massive fermions at all, but massless, neutral, photon-like bosons. They are born in nuclear violence, they travel across the universe without fading, and they carry away the exact imprint of their source energy. The historical mystery. The story begins in the 1930s with beta decay. Physicists noticed that when a nucleus emitted an electron, some of the expected energy was missing. This threatened the cherished law of conservation of energy. Wolfgang Pauli, in what he called a desperate remedy, proposed an invisible neutral particle to carry the missing share. Enrico Fermi turned this into a full theory of beta decay, and the particle was named the neutrino. For decades it remained a hypothesis. Then in 1956, Clyde Cohen and Frederick Reyners placed a detector near a nuclear reactor. They reasoned reactors flood space with neutrinos from countless fission fragments. After years of effort, they saw faint flashes from rare nuclear breakups. The neutrino was declared real. The standard model picture. According to conventional physics, neutrinos are electrically neutral, the nearly massless fermions, existing in three flavors: electron, muon, tau, produced in nuclear processes from stars to supernovae, capable of oscillating or changing flavor as they travel. They are unimaginably numerous. Every second, about 10 billion pass through each square centimeter of your body, and yet they almost never interact. But here lies the puzzle. Oscillations suggest neutrinos have mass, yet no experiment has ever pinned it down. This is the gap where an theory steps in. The Augmented Newtonian dynamics reinterpretation. In A&D theory, neutrinos are not fermions with mass, but bosons, photon-like couriers of nuclear energy. In beta decay, a neutron turns into a proton, and the leftover energy emerges as a neutrino, carrying a few hundred kilo-electron volts to a few mega-electron volts. In the Sun, proton-proton fusion produces neutrinos around 0.3 mega-electron volts, while later steps in the chain release neutrinos up to 15 mega-electron volts. In supernovae, collapse floods the cosmos with neutrinos carrying 10 to 20 mega-electron volts each, draining most of the star's binding energy. In cosmic rays, pions and muons decaying in the atmosphere launch neutrinos in the giga-electron volt range. In extreme cosmic engines, black hole jets hurl out neutrinos with tera-electron volt to peta-electron volt energies, detected today by IceCube. Mainstream physics calls these flavors. A&D theory says they are simply energy classes fixed at birth. Propagation. How do neutrinos travel? A photon spreads into a wavefront, its energy diluted across distance, obeying the inverse square law. A neutrino does not. A neutrino is the propagation of a single photon-like particle through the photon sea. Each segment of the medium holds its energy for only 10 to the power of -18 seconds before relaxing, but instantly reforms straight ahead, keeping the packet intact. Each one is a solitary carrier, traveling in a straight line with its energy undiminished. This is why neutrinos always move at the speed of light. And against all odds, they do not follow the inverse square law of propagation. Detection. If neutrinos don't lose energy with distance, why are they so hard to detect? The answer is geometry and timing. Each neutrino's path is vanishingly narrow, about an atomic diameter across, and each segment lasts only 10 to the power of -18 seconds. For a nucleus in a detector to be in just the right place at the right moment is astronomically unlikely. Yet billions pass through every square centimeter each second, so occasionally a collision occurs. When it does, the neutrino delivers its entire packet of energy in one blow, shattering a nucleus. Detectors do not see neutrinos directly, they record the wreckage left behind when one of these photon-like couriers finally hits. Kamiokande and IceCube. To catch these rare events, physicists built detectors on a colossal scale. Kamiokande in Japan, a tank of ultra-pure water deep underground, made history in 1987 by detecting a burst of neutrinos from supernova 1987A. It proved neutrinos streamed directly from collapsing stars. IceCube at the South Pole now uses a cubic kilometer of clear Antarctic ice. It has detected neutrinos with energies millions to trillions of times greater, arriving from blazars and black hole jets across the universe. In the mainstream view, these results confirm oscillations and mass. In the AND view, they confirm something more direct. Neutrinos are photon-like couriers that do not fade, delivering their full punch even after traveling millions of light years. Neutron stars and supergravity. In ordinary matter, electrons emit and reabsorb photons, creating fleeting alignments in the photon sea. Each tug shortens the distance between objects, producing ordinary gravity. In a neutron star, this principle is pushed to the extreme. Nuclear collapse releases torrents of neutrinos, not ghostly visitors but dense floods of photon-like couriers. Their numbers are so great, and their energies so intense, that almost every neutrino collides with a nucleus or brushes so close it triggers a violent interaction. The star begins to shred, and each violent hit releases reciprocal neutrinos, multiplying the cascade. The result is runaway. With every collision, more couriers are created, alignments tighten, and attraction intensifies. The outcome is supergravity, ordinary gravity magnified beyond recognition by the overwhelming density of neutrinos. Supergravity. It is the hidden engine behind supernova collapse and the crushing grip of neutron stars. Conclusion. For almost a century, neutrinos have been called ghost particles, invisible, mysterious, perhaps massive. And theory reimagines them, not fermions with uncertain mass, but photon-like bosons, solitary couriers of nuclear energy. They do not fade with distance. Their flavors are simply energy classes. Detectors see only the wreckage when one finally collides. Kamiokande and IceCube show that they travel across the cosmos unchanged. Neutron stars reveal their hidden power, the agents of supergravity. Thus the ghost particle becomes a messenger, not a mystery mass, but a courier of nuclear energy, and a key to the deeper order linking light, gravity, and matter itself.